When we introduce blockchain into an enterprise or government system, we don't magically remove threats, we reshape them. In this module, you'll see how distributed ledgers change the threat landscape, what new risks emerge, and how to reason about those risks in a systematic way. Trustless doesn't mean no risk. It means you're trusting different things. In a traditional system, trust is concentrated in a few components: the central server, the database, maybe an HSM. That creates single points of failure, but they're relatively straightforward to reason about, govern, and audit. With a distributed ledger, risk is spread across nodes, protocols, keys, and governance rules. The attack surface grows and liability shifts, from the server operator toward protocol design, consortium governance, and users' key management practices. To model threats in blockchain-based systems, you typically need two complementary lenses. Stride focuses on classic technical security failures: spoofing identities, tampering with data or code, information disclosure, denial of service, privilege escalation, and repudiation of actions. That's the can the system be broken or abused perspective. LINDDUN adds a privacy and data view: linkability, identifiability, disclosure, detectability, non-repudiation issues, unawareness, and non-compliance. For enterprise and government deployments, you usually apply both frameworks together to get a complete threat picture. Distributed control sounds safer than a single central authority, but it creates its own category of threats. If one actor can cheaply create many fake identities, they can look like an honest majority and sway decisions. If a few powerful participants quietly coordinate, they can censor or delay transactions. And if any coalition gains effective majority control, they can influence which history the network accepts as truth. In blockchain-based trust infrastructures, the real root of authority is the private key. Whoever controls that key effectively controls the identity, the permissions, and often the assets. Unlike traditional systems, there's no help desk and no password reset. If a private key is lost or destroyed, access to the associated assets or records is gone permanently. Because of this, secure key management, with HSMs, strong operational controls, and multi-signature governance, becomes absolutely central to any serious deployment. Smart contracts give us programmable trust, but they also create programmable risk. When code is law, any bug effectively becomes part of the contract's rules, and attackers can exploit it exactly as written. Typical weaknesses include reentrancy, arithmetic overflows, and subtle logic mistakes that only appear under rare conditions. For enterprise and government use, that makes disciplined, secure development, rigorous independent audits, and, where feasible, formal verification non-negotiable. Blockchain doesn't remove humans from the loop. It just moves the human risk into governance. Committees can be captured, approvals rubber-stamped, and upgrades pushed through without real scrutiny. Operational shortcuts accumulate, default settings, skipped reviews, inconsistent versions. If voting power is concentrated, a small group of validators can quietly tweak rules to benefit themselves. When you assess blockchain risk, treat governance itself as part of the attack surface. Immutability is a feature we usually celebrate in blockchain, but in regulated environments, it immediately collides with laws like GDPR that grant people a right to be forgotten. How can data be erasable when the ledger is designed to be append-only and permanent? The key principle is, don't fight the law with technology. Instead, design for deletion from day one by keeping personal data off-chain and making it practically unrecoverable through key destruction. Even when we encrypt everything on a blockchain, we still leave an invisible trail: metadata. Who talks to whom, how often, at what times, and with what transaction sizes can be enough to identify organizations or citizens. The payload stays secret, but the pattern can reveal relationships, sensitive workflows, or even ongoing investigations. Designing in this space means treating metadata as high-value data and planning for traffic shaping, aggregation, and selective disclosure from the start. When we move to a shared ledger across countries or agencies, the biggest new challenge often isn't technology, it's law. Regulators still ask classic questions. Who is the data controller? Which jurisdictions' rules apply? And who is liable when something goes wrong? Global replication collides with data residency and sector-specific regulations. For serious deployments, compliance has to shape the architecture from day one, not be added as an afterthought. When we talk about blockchain as the evidence layer, we're really asking, can these records stand up in court or in front of an auditor? A tamper-evident log is powerful, but it's not automatically legal truth. You still need provenance, context, and people who can testify about how the system works. The central challenge is bridging technical finality on the chain with legal finality in real-world decisions and disputes. In blockchain-based trust infrastructures, audit doesn't disappear, it evolves. Instead of pulling periodic samples from scattered logs, auditors can connect to read-only nodes that expose a verified, immutable history. On top of that, privacy-preserving techniques like zero-knowledge proofs let you prove rules are followed without revealing raw data. The big shift is toward continuous, programmatic oversight, real-time verification of compliance, rather than occasional after-the-fact checking. Think of your defense strategy for a blockchain trust layer as a three-legged stool. Technical controls are the obvious leg: HSMs, audits, network security, and hardening. They stop many classes of attacks, but only within the boundary you control. Legal controls define the consequences of misbehavior: contracts, SLAs, liability, and regulatory obligations. They create incentives and recourse when a consortium member goes rogue. Governance connects the two: voting rules, charters, onboarding, and offboarding procedures. Holistic security emerges only when these three reinforce each other, so any design decision should be tested against all three dimensions, not just the technical one. In blockchain-based trust, risk moves outward. You're securing collaborating organizations, nodes, and keys, not just a central data center. Identities and keys effectively become your perimeter, so key management must be engineered, not improvised. Design privacy up front, because immutability makes mistakes permanent. And treat governance as a security control. Taken together, your North Star is always risk-informed design. You've just mapped how attackers, mistakes, and governance failures could break trust. Take a moment here. In the next module, we flip perspectives. You'll design the actual trust architecture: identity, data, and governance, so those threats become design inputs, not surprises.